Good afternoon, everyone. This is our last lab for this semester. Just a reminder, the lab report is due next week, next Tuesday. Okay. Let me share my screen. Okay. Wait, today we have lab 6 because last 2 weeks ago we did lab 7. So this is our last lab. If you have any questions, just unmute yourself. And I can answer the chat. So this is our last lab for this semester. We will have this lab report due next Tuesday. Then, yeah. Any questions? And please submit if you miss any report for the previous lab, please submit them as soon as possible. Because I think after Tuesday, I think by the end of next Friday, like we have all the TAs have to submit their your grade to the department. So after that, you probably don't have a chance to get graded. All right, let's get started. Turn off my video so you can focus. Okay, so this is for the simple harmonic motion. And if you go to the simulation page, so basically, this is like what we do for today, the intro and the vectors lab, and we will go through one by one. Let's see if someone is coming. All right. Okay, so So we can compare the two. We can just follow the instructions to do the lab. So first, we have this. We just revisit the Hooke's law. The force applied on the spring that equals to the negative kx. X is the so so the minus sign means it's a restorative force moving toward its equilibrium or rest position, and the k is the spring constant, and the x is the extension.
You're trying to show something. We can only see your desktop right now.
You cannot see.
Yeah, I mean, we can only see your desktop. I don't know if it's in a different window or something that you're reading this from.
Oh, sorry. Let me.
Yeah, no worries.
Um, oh, sure. So you can see the screen now.
Yes, now we can see it. Thank you.
Thank you. Thank you. So what I just said is like we just before we go, so all these equations or like the simulations will be relevant to the simple harmonic motion. So before we start, we just revisit some like just get some warm up and revisit some like knowledge we know before. So the force, like the force on the spring, we have the Hooke's law, Fsp equals minus kx. And the minus sign means it's a restorative force. And the k is a constant, x is the extension of the spring over its normal length, or like you measure it after it moves away from its equilibrium position. And also we have the F equal to mg, the gravitational acceleration. So the g here we use 9.81 meter per square second. So for the simple harmonic oscillation, angular speed omega, and we know omega equal to theta over time, and theta is the radian, like the total angle you crossed. Then you divide it by the time, it's your angular speed, and the periodic time, which equals to periodic time. It means the time for a complete oscillation. It also equals to 1 over the frequency. Frequency means how long does it take for one circulation. And therefore, okay, t equal to 1 over f. The angular speed omega is the 2 pi over t. T is periodic time. 2 pi is the total circle. And the acceleration a equal to minus omega x. So here, so I did, so I try to derive it how we get this, but apparently they postulate this acceleration from simple harmonic oscillation. There are two. Sorry about the barbs. So there are two types of the simple harmonic oscillation. One is like you have a spring and you tie something like this. Another is like you have let's say you put a box in a floor that has no friction, but you keep moving back and forth. So they got this acceleration by no. Let me show you two tabs. Motion. Simple. So they got this the acceleration from this one. So let's say so we have so let's say x. This is r. This is x. This is moving, and they have like an angle. Let's say call it theta. So whenever you move, let's say this is the beginning, and then you move. Let's say for a certain angle is theta, and then you calculate x equal to r cosine theta and y equal to r sin theta. And then when you try to derivative its acceleration, then you have you basically you use the speed, use the linear speed. So you have the velocity. So you have velocity minus a omega sin omega t, and you do the acceleration. You do the mass for acceleration, which takes the omega one more time from here, and then you get a omega square cosine theta. But this is for like this is, you see a ball is rotating in a circle, but what we do here, sorry. What we do here is on the string. So you don't use the angles anymore. So you just get a minus omega square x. So this is what I found there relevant. If you have any other explanations, is also as long as it makes sense to you, it's just like help you to understand. As long as it makes sense to you, it should be fine. So we have this acceleration equation, and then we can also apply the force, because the simple harmonic motion, the only force applies on the spring. Let's start. Is, let's say, put it here. Stop. So the only thing you know the only force applies to the string. The string is the gravity of this thing. What do you call this? The box. Wait. So this is so they have an equation here, which is the force equal to ma and equal to fsp, and the ma equal to mg, and also a. Okay, so I think where I'm gonna say, so ma also equal to, you see that acceleration a is minus omega square x. So you put this a, ma, and m times this a equals to minus kx. So you get a derive the omega equal to k over m, do the square root. Also k equal to m omega square. So this is just the so you know one way how to calculate the spring constant. So this is k equal to m omega square, and so this is for simple harmonic motion. Position of oscillator is given x equal to x0 cosine omega t, and the velocity of the oscillator equal to v to the derivative to t, right? The x to the derivative to t. So it's minus x omega sin omega t. And the acceleration of oscillation, you do the derivative of v, so you get the a double derivative. You get this one. And the potential energy of a spring, E potential is half kx squared. X means the extension of the distance. And the same as work W done by spring kinetic energy, by kinetic energy of oscillation mass. What? Same as work W done by spring kinetic energy of oscillation mass. So this means the spring kinetic energy equals to 1 over 2, which is half mv squared. So this is just like a warm up. Like we know what kind of equation we might use, and we may need to calculate while we do the lab. So let's start with intro window. So use spring 1, and for the experiment. Select 3 as spring constant for spring 1. 3. So like if you look at this, the lab, the intro, you see here's some weights and excuse me. So you can adjust the spring constant. You see, it's 1, 2, 3. We can do it. Maybe you cannot change. Or you can do this. You can adjust the spring constant if you drag them. So we just select 3 as spring constant, 1, 2, 3. But we don't know the number. Here you can stop. This is spring constant adjust for spring 2. And so the gravity, this means the gravity from Earth, which we use 9 equal to G equal to 9.81. And the damping is 0. So damping means like we have like some frictions, or you kind of something like the energy will be warmed out. And we have a ruler and we have a timer. Then we have this natural length. This is just for measure the spring. Let's say natural length. So the spring natural length is here in the blue line, and the equilibrium position is when the spring gets to the equilibrium, and the movable length is here. So let's say before we put the weight on the spring, it's like the natural length and the movable length. Let's say we put the weight on the spring, and you can see, okay, let's put a ruler here. So you can see this is the movable, this is the equilibrium position, this is a movable line. So this means there's another line, the same length between the red and the green will be like a, okay, let's say the green line is a mirror. So they will, if this is a mirror, then there will be another red line here. This red line is also indicates the distance from the equilibrium position. But yeah, you just try to play around, and you see here it's normal. This normal speed, and this is slow speed. Let's click slow speed, so you can see it's moving very slow. So if in the later we're gonna use this motion to try to measure the distance or something, we can use a slow motion. But let's back to the normal. And yeah, so let's look at the menu. We use the spring 1 for this experiment, select 3 for spring constant. We have selected 3 for the spring constant. The default gravity on Earth. So we have the default gravity on Earth. Right the corner, natural length, equilibrium position, the ruler and stopwatch for linear and the time measure respectively. So basically we use the natural length and the movable the equilibrium position. Select ruler. You just put it here. Select 25 gram to 50 gram mass and attach to spring 1, press red button at the side. So after we attach this this 20 to 50 grams weight on the spring, we click stop, and then measure and record. Press stop and measure record value for extension of spring 1 with 250. So extension is from the natural length. So you know, before we applied the weight, the natural length, this is the natural length. After we applied, it's here. So it's 41, I would say it's 41 centimeter. So this is for, you measure the extension then pull the mass downward away from its equilibrium position for extension between 10 or 20 and 20 centimeter and release to begin oscillate. So now we press it stop, so it stopped. So if we pull, so you could record this 41 centimeter, and if we pull like 20 or 10 to 20, so we just say movable length. Just try to pull a little bit like this, and then you record. Use a stopwatch to measure 10 oscillations. So you can count, let's say, when the weight goes up, then we start count and to count for 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's like 13.16. Yeah. So this is for 10 oscillations, and you do 2 trials to get the average of these 2 rounds. So then you take so this time, and you divide it by 10, you will have a periodic time. That means how long does it take for one oscillation, right? And you use this one, and you use and you determine the spring constant using 2 different methods. One is K equal to FSP over X. And this is FSP is the weight of this. So 250 grams is the M. So mg divided by X. X is extension. So basically it's extension from here to here. So from the natural length to the equilibrium position, this is the extension, and the K equal to 4m pi square over t square. So this is another way to calculate the constant. And you put you already, since the first step, you already calculated the periodic time. So you can use this one, and a 4m pi are constant. You just put the periodic time here, then you can calculate the constant, spring constant. Any questions so far? Okay, let's start. Okay, let's go to, okay, we still have a few questions left. So you can see by using 2 different methods, you can see if there are any difference and why there's difference, because like your measurement errors, some errors are inevitable. So it's not like because you didn't do it good, it's just because everybody, like when we say something, everybody has their own like preference, or they maybe when we read, when I read the extension is 41, but when you read it's maybe 40.9 or 41.2 or something. You just everybody has their own like so everybody's different. So that means like you can have an error. It's inevitable. And determine the percent difference, which means you divide it by, so you use K1, let's say this K1, this K2. Is it K1 minus K2 divided by K1, this is the percent, and times 100%, and you will get a percent difference. And since from this, you already calculate the K, and you just, if the percent difference is less than 5%, you take an average of this 2K, and you determine use this K to determine the unknown Hooke's masses. You determine the Hooke's masses of these three, the red, green, and orange. So how you gonna so if your calculation is bigger than 5%, you just use K1 to calculate this unknown masses. So how do you calculate this the mass? So basically, what you do is, let's say I put this back. Okay, so the constant, the constant what I calculate is 6.1. So let's say we just use 6.1 this for this K, and then we put this one here. Then we have M we don't know, Mg we don't know, but but we can know the spring constant by calculate Kx. So which is we use this K times the extension from the natural length to equilibrium position, this extension. So this distance times K is F. And then F divided by G is the mass. So basically we use, let me see if I can draw something. So here how we do that. F equal to mg equal to kx, right? So you can do you can use K1. You already calculated is equal to 4.125, and the x you can measure is 11, 12, 13, and the x. Just make sure you make the unit is unified. X is 13 centimeter, and then the g equal to 9.81. And then you can calculate M. So you calculate 3 M's. So, I have to stop. Okay, so this is any questions for this one?
I have a question regarding the figuring out K via the force of the spring divided by X. The force of the spring divided by X
is minus Kx, you mean?
Right. Is force of the spring is minus Kx divided by X is just going to give us our K. But I'm not sure how we're supposed to figure what we're supposed to do to plug in for the force of the spring to calculate that particular method.
Okay, that's a good question. So when you look at this spring, so when we try to define its minus or positive, we just need to find the how to say, so the spring, let's say for this object, for this mass, so there are two forces this object is has, right? So one is the gravity, one is the spring pulling up.
Oh, got it. So what we're doing is we're saying it's mg is the force of the spring as well, and so that's what we're using for that.
Yes.
Got it. Okay, I'm good. Thank you.
Wait, before we go on, I was just I was doing it as we were going through it, and I'm just maybe it's the units is what's messing me up. But when I did the to figure out the spring constant, like we were just talking about, I got two very different answers, like significantly different answers. So I just want to
also had to calculate. Tell me what's your answers.
So like I did the so for part A for periodic time, I got an average of 12.4 seconds for 10 oscillations. So T is 1.24, right?
Yeah.
Want to make sure. Okay.
Yeah.
So I did that, and then so for the first method of the spring constant, K equals force of spring over X. So K equals mg over X. So should M be in kilograms and should X be in meters? Because then that's going to work.
Yes, that's correct.
Okay, so So it's like 0.25 times 9.81 divided by point, because that's centimeters, right? On that little ruler. Point 0.15 meters. Let me just
divided how many meters?
0.15, right?
You mean you measured? I mean, you are calculating the 250 one, right?
Yeah, like if yeah, that's what I'm saying. Like I pulled mine down 15 centimeters, which would be 0.15 meters, right?
0.15 meters.
Yes, that is correct.
Okay, yeah.
Like, let me see. I just did 0.15. Why is 0.1? Why is not 0.4?
Because x is just, it's the distance it was pulled from its equilibrium position.
Yeah.
So that would mean 50, like, and it said between 10 and 20 centimeters. So I split the difference. So I did 15 centimeters, right?
It's supposed to be like you measure the distance between this natural length. This is the equilibrium position.
Yeah, I pulled it. Oh, that's, maybe I'm doing that wrong. Yeah, that very well could be it.
So you need to use the distance. Yeah, this is like a very easily get confused. So when you try to measure, let's say before we put this mass. Okay, stop. I cannot catch it. So before we put this mass, the mass on the spring, this is natural length.
Okay.
Right? So then after we apply the mass here, and then you see the equilibrium position. So this equilibrium position is not the farthest position. It's just the middle. So that means the extension. So you see after I let it go, the mass goes farther down. So that means, I mean, the equilibrium position is the middle, you know.
Yeah, that's maybe. So I just want to clarify then. So x in that formula, the force of the spring, which we substitute mg in for that, so we get k equals mg over x. X in that scenario is going to be the distance from the natural length to where we pulled it to, because that's what I was doing, it from the equilibrium position to where we pulled it to, and obviously that will give me a different answer. Let me
yeah,
instead of like 0.15 meters, it'd be more like 0.55 meters from the natural length.
Oh,
right?
They don't have the same. Yeah. So here, what I read is 41.
Yeah, no, I get that.
It's only to the equilibrium is the point. It's not to where you're pulling it to. You're just getting it oscillating, but for the purposes of the force spring over x, you're just actually going only from the natural position to where its equilibrium position is, because that's where they're balanced. That's where the weight of gravity is equaling the force of the spring, and that's why it's not going up or down.
That makes sense. So it would be 0.4 meters then.
Right.
Yeah.
Okay. Let's see. Maybe that make a lot more sense. That divided by 0.4. Yep, there we go. That makes way more sense. Thanks for going over that.
Okay. Any other questions? Okay, no other question. I need to erase this because that's maybe too much. Okay, so this is for the intro, so everybody get themselves familiar with the lab setting. So next we will go to the vectors. So you see, you can just click here. You see intro vectors energy lab, but we don't use the energy. We only use the lab which has the energy. Okay, so let's go to the vectors. Vectors is so you just answer these questions, and so this vectors section help you visualize the oscillation in play. Select displacement, mass, equilibrium, velocity, acceleration, gravity, and spring. For first round, leave gravity as Earth. So still we have different options. We can make the displacement. This is natural length, the equilibrium. Okay, so actually I want to say here. So displacement, you can see the displacement. This means the displacement, and you see the mass equilibrium is in the middle. It's not like in the this is how you measure x extension. Even it didn't draw exactly in the middle, but yeah. So the gravity in Earth, and then you can click the velocity, acceleration, and the forces, gravity, spring. And let's put a mass on the spring. So we still use it. Okay. So you can see all this are indicating the velocity. Let's see if we only look at velocity, you look at the green arrow. So you see like it's like going very far down. Let's see, put it on a slow motion. So you see here is 0 and start increasing the maximum and decreasing to 0 and going up. So so this is, you can observe from this vector and answer these questions. So the first question, at which point is the velocity minimum or 0? So which point the velocity, you can see which point the velocity is 0. It's either the bottom or the top, right? But both the bottom and the top, not either. So it like reach the velocity to 0. And at which point, wait. No. Yeah, I think I'm right. I got a little bit confused when I see the weight is moving here. I was like, the speed is increasing. So at which point is the velocity maximum? So at which point the velocity is maximum? Okay, let's don't look at this. It's a little bit confusing. It just so if we look at the motion, we know. So let's analyze the process. Like when we put the mass on the spring, the gravity at first the spring, like the first spring didn't stretch a lot. So the F equal to S, F equal to kx is not a lot. It's smaller than gravity. So the gravity is bigger than, so the net force is basically the gravity minus kx. So that's the total gravity, the net force. The net force is positive. It helps the weight to increase, to gain some accelerations to increase the speed. Until, so the speed is increasing until the mass reach to the equilibrium position, which means that when it reaches to the equilibrium position, the the gravity equals to the spring constant. So at that time, the net force equal to 0. So after it is stretching more and more, the spring force is greater than the gravity. So that in that sense, the speed of the mass is decreasing. So after the mass across the equilibrium position, the speed is decreasing. So then it's decreasing until to be 0, and then the spring just totally, the spring will draw this mass up. So then when the mass reach to 0 in velocity, then the velocity will change the direction, start increasing again. So increasing until it reaches to the maximum speed in the equilibrium when the spring force equals to the weight. And then when it goes up, because it is still at the equilibrium position, it still has the maximum velocity, which leads to the mass going up. So when the mass going up, the gravity is greater than spring. So then the mass starts decreasing its speed. So basically, you can consider there are two half process. One is like in this half, for the first half, we know the gravity is always greater than the spring. But in the equilibrium position, the gravity is equal to the spring force. And after the mass crosses the spring equilibrium position, the gravity is equal is smaller than the spring force. Hope I don't confuse you. So this is how when we analyze the force and the velocity, this is how it works. So then after we understand this, we can answer these questions very easily. I don't really recommend you look at this, even it helped, but because it was not a very, it draws not equal. So you can see this is, but it's up to you. You can just analyze through your physical force analysis or through visualize them. So as we answer, does it make sense to you? The two parts of force, like a motion, parts motion. Okay, let's look at these questions. So when the velocity is minimum or zero, so when the mass reach to the bottom and reach to the top, it's zero. And it's zero and start turning the directions and then start increasing. Like the same here is reach to before the mass reached to here and then the velocity pointing this way, pointing down. But after it reached to zero, it start pointing up. And as same as here, so the velocity, the mass is when it's going up, is the velocity is pointing up. But when it reaches to zero, the speed start changing directions and pointing and start increase pointing down. At which point is the velocity maximum? So the velocity is maximum when it reaches to the equilibrium, because that at that time the acceleration acceleration speed is zero. So this is all the effort from acceleration to put the speed to the maximum. At which point is acceleration zero, which is also the equilibrium. At which point is acceleration maximum? So a maximum is like when the speed start changing position, changing directions, which is the top and the bottom. Is gravity ever zero? Gravity never be zero, right? Is spring force ever zero? Yes or no?
I would say no.
Spring force never zero?
Because the spring force, I'm sorry, I misunderstood. The spring force can be zero.
Yeah.
But the actual tension from it is not ever going to be zero. It's just going to be offset by the other things.
You think in this like motion it ever be zero or not?
No.
No. Let's look at let's try to see. So this is start, right? And so like when the mass reach to the very top, do you think this is okay? So let's do like force analysis when it's reached here. So you tell me how many forces the mass has.
It just has the gravity pushing down on it. It doesn't have the spring force because there's nothing else the spring's going to do. That's as far as it's pulling. Right. So the spring force is zero there.
Yeah. So yeah, that's right. So when the spring force is totally depends on how much it's stretched. If there's no stretching, it's like in the natural length, then there's no spring force. So the spring force ever could be zero when it's on the top, when the mass is on the top, right? And G, what happens when spring constant is increased? So spring constant, what it affects to? So it only affects to the F, which is the spring force, which can be used by F equal to minus kx. So if the spring constant is increasing, okay, let me write it down to visualize. So F equal to, so since we just analyze the force, we just, I just drop minus, but when you, I just draw kx, okay. So when this one is increasing, let me see if I can. When this one is increasing, that means x, if x remains constant, then f will be increasing, right? So when the spring constant is increased, that means the spring force will be increasing. What happens when gravity changes to Moon, Jupiter, planet X? Okay, so we have gravity. Gravity only affects to the gravity is affected by the gravity acceleration. So because we know in the Moon, Jupiter, or planet X, we have different gravitational acceleration. So this is the only thing that could change change the gravity as well. So you see here, I have to stop annotation. Erase them. Okay, I'll erase them. Then, so if we see here, Earth, and we can choose to Moon, and we choose to Jupiter or planet X. So before we go, how are we gonna observe? So before we are on the Earth, so this is natural length, and this is the mass equilibrium, right? So if we see, we change to Moon. Oh, you see the equilibrium is smaller. That means you don't need that much stretch. Stretch you can equal to the so like a equilibrium, at the equilibrium position, you have F kx equal to mg. So when the kx doesn't change, g doesn't change. Sorry, m doesn't change. When the when you need a smaller x. Okay, let me write down. Annotation. So here is f equal to kx equal to mg, and the g when the stretching. So this is x. When x is smaller, when x is smaller, that means g is smaller, because m and k are constant. So you just compare this. If x is smaller, g will be smaller. Let's see. Can I change? Let's do it. Yeah. Let's change this. We change to Moon. Let's change to Jupiter. Wow, this is the equilibrium position. So that definitely means the x is greater. That means g is greater. It's increasing. And then let's see planet X. Well, planet X. Oh, okay, let's compare to. Planet X is in between Jupiter and Earth, I guess. Yeah. So the planet X, the gravity. So how you answer this? What happens when gravity is changed to Moon and Jupiter and planet X? So when it change to Moon, the extension will become smaller. It's smaller than on Earth, and then this one is how you answer is more proper. So basically, I think the conclusion I can get from this is when the gravity change to Moon, the extension of the spring is smaller, and when it changes to Jupiter, is the extension is increasing. The extension of the spring is increasing, and when it changes to planet X, extension is changing between Earth and Jupiter. Does it make sense? It's like it's a very objective question. I mean, you can answer anything you observed. And determine the value of gravity on planet X. So how we determine the value of little g? So we have k, we know k, and we so basically you can calculate on Earth. You calculate k on Earth. You will have this g, mg. G you also know is 9.81, and you can calculate the k constant. And because this k constant is a physical property, so it doesn't change whenever either it's in the moon, in the Jupiter, in the planet X. It doesn't change. It's just like a property. It's just like your mass. It doesn't change. So then you use this one, use this constant, and the X you can measure when you change to be in the planet X. Oh my God, I feel so dizzy. So you measure, you have the ruler here to measure the X, the extension, and you also have the mass, mass 250 gram. You just make sure to change to kilogram, and you can measure the little g for planet X. So my calculation is like 17.4, but maybe you have a different S. I mean, like it's very close. So any questions for this section? No question, we move to the lab. How many left? Okay. So we go to lab. So click check boxes on top right, natural length. Okay, so every time you just click them. Mass equilibrium. So the ruler stopwatch for linear time measure respectively. So spring constant damping such that spring constant is greater than damping. So I would suggest you just change damping to 0, because if you have a damping, that means you have like energy usage. So yeah. Select a 100 gram mass attached to spring, adjust mass measure to value greater than 250. So when you put here, and you can see here's the mass, you can adjust them. So this is 100. Okay, stop it. You can adjust to a value greater than 250, 250, 250. Okay, adjust to 60. Okay. So you greater than 250, press the red stop button at the side of the screen to stop oscillation. Measure and record value for extension spring mass attached. So here you measure. So here's a natural length. You still do the natural length. Just make, because this ruler is transparent. You can really read the lines. So this is from, make sure. This is 1, and then this is 54 centimeter. So extension X is 54, and the mass is 258 gram, and you have G, and you can calculate K, right? You can calculate the K. Okay. If you look at the energy graph, so this is kinetic energy because it stops, so there's no kinetic energy, and this is gravity energy. You see how we gonna look at the gravity energy? This is the hat 0. If this one is here, the gravity 0. Gravity energy is gravitational energy is 0. But when it's increasing, so this, how you calculate this one is like by mgh. The elastic energy is half mx squared, and the thermal is like when you're like, let's say if you have damping energy, you really cannot calculate. Just like this is the energy usage, like a turn to thermal. But we don't want to, because it's very hard to calculate, so we don't use the damping here. We just set to 0, so it's easy to visualize and do the calculations. Okay, let's continue. I just want to introduce this energy table, like how we get this get the energies, and then so we determine the periodic time. Also, we measured vector and the record value for extension of spring. So we use this one to record this extension of spring. Pull mass down away from its equilibrium position for extension between 10 and 12, release it to begin oscillation. And use stopwatch time for 10 oscillations. Okay, here. Movable line. I don't know, movable lines. So let's say from, okay. Let's try to measure how to, we pull something. Like you just try to pull a little bit. You see what I measured here. What I measured here is try to use this line, displacement. I want this is 0, and then I can measure 10 to 20 centimeters. So I just see if this line reached to here sometime, like this, and then it's oscillation. It's start oscillation. To try to measure the periodic time, I still count the same when the mass is on the top. Let's start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's 13.04. So you divide it by 10 is 0 periodic time. I'll calculate spring constant. Okay, spring constant, we can use M, which we know, G, we know it's on Earth. X, we know, we just measured. It's like for 54, right? And then you can calculate the K constant. Determine energy of spring at top of the oscillation. Energy of spring, so when it's on the very top, when the spring is at the very top, there is no stretching, so the energy of the spring is 0, right? So when it's in the equilibrium, this one, you can measure this. This is 54 centimeters, so the energy, so which equation we use, I just write it down. I need to write it down, so you don't get confused. Energy, when we try to use the energy of the spring equal to 1/2 kx squared. So this is the equation you use to calculate the energy.
Question. That's for kinetic energy. Shouldn't we be also taking into account potential energy?
The kinetic energy should be kinetic.
The spring kinetic energy is the 1/2 kx squared.
Yeah.
But there's also potential energy, which is where all the energy is with the spring at the top of the oscillation. It's all in potential energy.
So you mean the energy of spring, you want to calculate spring energy plus the potential energy?
Well, isn't the potential energy part of the spring's whole energy?
That's not, right? So when you're, like when we see potential energy, we are looking at this, the object.
Okay.
So when we say, okay, so how we see it, right? Okay, let's just like it. So when you see the mass is moving, so you can see here, it has kinetic energy, the gravitational energy, which is the potential energy, the elastic energy. If you say gravitational energy, which is the potential energy, is part of the elastic energy, then it wouldn't like at least two separate energy.
Okay.
Do you understand, or you just like don't want to?
I'm still, I thought that they were like part of the total energy. But there's
Can
another
the
question
photon-
later that's the total energy of the system. So I guess this energy is just talking about the kinetic energy.
This is talk about the spring, the elastic energy.
Right. It just didn't clarify that, but I get now. Okay.
Okay. So like when we calculate the energy of spring, this means the elastic energy. So you use this equation half kx squared, and you calculate on the top, which x is 0, and equilibrium position. As you measure the distance between the natural length and the equilibrium position. And it is the lowest point of the oscillation. So this is the x, the extension is double of the distance between equilibrium position and the natural length. So it just times 2, right? The x times 2. So here you will have a square root. Not square root, sorry. A square. And determine total energy of a system. So in this question, we started to calculate the total energy of a system. So as you can see here, because we don't have damping, so the total energy is constant. But if we have damping, the energy has you have energy turn to thermal, so the energy will be decreasing. Make sure if I cannot. So okay, so since it's the total energy is constant, you can pick any time, you can pick any position at the very top, at the very bottom, and or in the equilibrium position. You just calculate the total energy. So what I would do is try to get the equilibrium. I would choose equilibrium position, because at the equilibrium, I would choose it on the top, because at the top the kinetic energy is 0. So we don't need to calculate what the kinetic energy. So because the velocity at the very top is 0, becomes 0, and you just calculate the gravitational energy and elastic energy. Elastic energy here at the very top is 0 too. So the total energy will be the gravitational energy. So you just measure the height from here to here, right? Okay, let me. I really. So I will measure the height. So this is 90. This is 100, right? 100. So because I cannot turn around, I guess I cannot turn around. Yeah, I can only move translational. So if we calculate let's say this is 0, then this is gonna be 90. So 95, 6, 7, 97. So the total height is 0.97 meters. So you just when you calculate the total energy at the very top, you just use this gravitational energy to calculate the total energy. Show the work done on spring is equal to change in spring potential energy. Work done on spring is equal to change work done on spring. So basically, the spring potential is work done. So what work is done? It means the gravity. The work done on spring is equal to change. So the work done to the spring means it's a gravitational energy change. It equals to the spring constant. Spring energy change. So you choose 2 positions. You can choose So you can choose two positions, and you try to measure x1, x2, and then you measure the distance between them, and then actually that delta H is also like the absolute value of x2 minus x1. You just make sure if they're equal. I think let's take an example. Let's say we measure from the top to the equilibrium. Okay, this one. So we want to say we want to calculate so the first one, this one, the top will be x1, the equilibrium position x will be x2, and the x1 we know is 0. So so if we calculate this part, then we just this one will be 0. Then this one be half kx2 squared. So this will be 54, right? 54. If someone has calculator, can do a calculation. So the constant k, if I calculate correct, do I have this value here? Okay, I have a constant for 6.06. I could be wrong, but if we calculate for the k, let me use calculator to see. 6.06 times this 0.54 times 0.54 times 0.4 divided by half. .88. So then if I calculate this one, mgh, mg, it's 258. 0.88. Remember this value. And if I calculate this one, mg, 0.258 times 9.8 times 0.54 mgh. Kx. What's your calculation? Why get a different value? So what I get for mgh is show that work done on spring is equal to. So I think that it's not like I think what I said is not correct. So you cannot choose two random positions. Work done on the spring, that means you only choose two positions. One is when it's very top, one is very bottom. So this is the work done. Because at this time, if we choose the equilibrium, it has a kinetic energy. We cannot do that. So we choose the top and bottom. Top, then kx still 0, and kx1 is still 0. X2 is 108. So 1.08. Because we have half is 54 centimeter, right? So the total will be 100. I think it just doesn't make sense. So what I want to say here is like when you measure the extension from the top to equilibrium, it's 54 centimeter. So that what we would assume is when the mass reach to the very bottom. So the mass, extension will be this half times 2, which is 54 centimeter times 2. it's 108 centimeter. But apparently when we measure from the height, 0 to here, it's not even more than okay. So it's definitely more than 100. So this is 100 centimeter. It's more than 100. How do we measure this? Okay, so I think one solution I came up is because this mass is definitely lower than delta H. Oh. So you can use the delta H. You just use the from here to here. You can also use 54 centimeter times 2. Let me calculate if it's correct. So if I use 6.06 times, are you guys following me?
Yes, I'm trying to figure it out myself while you're doing that.
You can use the constant as 6.06. This is what I calculated. 6.
Yeah. No, I think you're right about the spring constant. I got the same thing.
Okay. 6.06 times x, which is 1.08 divided by 2. So 0.258 times 1.81 times 1.08. Well, it's not exactly the same, but very close. Oh, wait. The key to solve this question is to find the right position where we're going to find this position.
Professor?
Yes.
I think it's the equilibrium position, because I was just messing around with the formula, right? So
Yeah.
if you put like the K equal to mg over x and plug it into the kinetic formula for the spring, elastic energy formula, right?
Yeah.
You're gonna get mg x over 2, and that would be half the length of the elongation. So that would be the equilibrium position.
Wait. Equilibrium from top to the equilibrium position.
Yeah. So what I did was, like before you said, like I used the formula kx equal to mg, right?
Mm.
And then I solved for like K. So I said mg is divided by x, right? I plug it into the formula that you have down there.
Yeah.
And then I got mg x over 2. So that shows that it's supposed to be the equilibrium position should be measured at. That's what I think. I'm not sure though.
Okay, let me write down what you just said. So you said like because we have f equal to px equal to mg,
Yeah.
and so we have k equal to mg over x, right?
Yes, and then you plug it into the half. So it'll be half mg over x squared, and then you cancel.
Wait, sorry. Oh, I see what you mean. Oh, I see. So like if we put this one into here, then it'll be mg dot h.
Yeah, so basically it would equal to the same thing, right?
Yeah, and the k mg over x
Times
and 10
x squared. So basically we cancel out x, so you get mg x over 2.
Yeah, so mg will be canceled off, and then delta h equal to half x, right?
Yeah. Yes, basically.
Yeah.
So it would be the equilibrium position then. You would have to measure it to get the work done.
Oh, let me think about it all first. So do we have something there? mg, yes, this is correct. Or let's see if it's from the top to bottom. So half x will be equilibrium, will be in this half, right? Okay, I think. Okay, so it depends on x. If we say x is in the equilibrium. So let's say top, this is definitely x is 0. We know that. If it's equilibrium, this is called x, and delta h will be half of them, right? But if we move the x to the bottom, then the delta h is half, still half. So
yeah, exactly. Yeah, that.
But it doesn't, at least it doesn't like make sense to me, because x is, if we say it's equilibrium position, then x is here. So h equal to delta h equal to half x, which is here, which is in half distance between equilibrium to the top. I think it's somewhere it says the work done. Let me just revisit the definition. Work done. Somewhere in the beginning. Potential images, somebody work done by spring. Same as work done by spring. Oh, I think that when I read this, I just combine these two together. So that's why it doesn't make sense to me. It's just two separate things. So this one is equals to the work done by spring. like I did before. Yes. 22, 21.
Correct me if I'm wrong, and I very well might be wrong, but I don't know if we can combine the negative kx in that way because the x2 and x1 are not the same thing as the x from negative kx. Because this is an integration form of an x that's moving, as opposed to the negative kx is the distance between the equilibrium and its point of rest, right?
Point of what?
From the spring's natural point before anything is attached to it.
Yes.
So that's what x is, but
Yeah.
not the x1, x2. The x1, x2 are different lengths, so you can't combine them in that same way, right?
Yes.
They wouldn't cancel each other out.
Yeah, I mean, like x1, x2 are two positions, right?
Right.
Yeah.
Which
Why
means,
cannot, you mean, what do we cancel?
well, when you did the other equation of the mg delta h is equal to 1/2 mgx x squared, mg over x times x squared, that over the mg over x, that x that you have there is not the same thing as the x squared, because that x squared is a distance that isn't just to the equilibrium point. It's to wherever that second point
that's
is.
what we just said, like this one, x, if x is means like from the equilibrium. Yes, I understand you. So this one we are still kind of have doubt. So like anyone can tell us what their understanding about this question. Show that work done on spring. So this is equal to change in spring potential energy. Spring potential energy change we can understand just like a measure two different positions, x1, x2, and the work done. That means the gravity down to the spring. I mean, not the gravity down to the spring, the gravity down to the mass, and the mass kind of have a pulling force to the, like if we analyze the spring, spring has its own like a spring force and also has a pulling force by the mass, right? So the work done on spring means the mass down to the spring. So I guess let me do it. Okay, then we try to, let me search. Okay. But like our understanding is right. Like when we are when we pulling off the spring, so the only work done is through mass's gravity. So it's mass's potential energy. So it's mgh. But whether they are equal or not, there are so many factors you have to consider, because here apparently, okay, I want to change this question to be like, try to calculate the work done on the spring and calculate the spring potential energy change. So there will be two questions to answer. So maybe they are two very different, they don't equal to each other, because so when we try to read the, try to do the measurements on the screen, there is just like, it's not very precise when we try to calculate everything. And let me see. And if you look at this energy graph, this gravitational energy could be like negative, which means it reached to bottom of this, like even lower than the hat 0. So definitely, but how you measure that? It's very, I don't know how to measure this one. You just measure this part, or because I don't, if we measure this from this part to start. Let me see. I think maybe we can measure like from bottom to bottom, like this is the very end. It reached to that much. This is the, okay. So I think, okay, so this is the very top, right? And then you see how low you can go. Okay, 79. So 79. Try to do this. This is 79, and this is 71, 2. Okay, so one height delta H should be 72 minus negative 70 minus 7. So it's MGH is, what I want to say is, oops. Okay, let's just do one more try. I think we spent too much time on this question. So my point is, so we see from here to here is 70. You see it reached to 79. So this is the total height. But since we have the height here is 0, so anything above here, the height is the height. H1 will be 72 centimeter, and the H2 will be minus 79 minus 72. 79 minus 72 centimeter. So this is when it reaches below. So when you try to do MGH dot H, you try to do this MG dot H, and then try to calculate the x1 and x2. So apparently x1 equal to 0, and the x2 equal to fires. You measure this green line, I guess. Measure this green line, because this green line means displacement. Measure this green line. Oh, I have to. And it's 81, 82. 81, 82. 81 centimeter. Try to do this. I mean, you don't need to make them equal. You just calculate the work done on the spring and try to calculate the spring potential potential energy change. So this is the thing you will need, and try to see if they're equal or not. So we don't have to like prove they're equal. So there are so many factors to have to consider when we read from the graph. It's not like a very precise tool we use. Does it make sense to everyone?
Yes.
Yeah. So I was trying to figure it out, and I think it's honestly just it's going to be the reason that it's a little off is that it's like user error when we're measuring the time, because basically, so if we want it to be equal, the mg delta h is really easily calculated. It's got to be k. K is the one thing that can change because the change in height is really easily measurable. The difference between x1 and x2 is really easily measurable. I did the 0.54 like we've been doing this whole time. And so if you do all that and you leave k, try and figure out what k would need to be in order for it to be equal, k would be equal to 9.37. And so then if you go back to that formula where we derive k from, and you substitute 9.37 in for k, and then you isolate t, you try and find t equals 1.09, and we had originally done 1.3 as t. So it's that small of a difference, and that changed everything.
Yeah.
That's like, I really believe that's all that it is that it's just when we're calculating t. So like I said, if t is 1.086, then k becomes 9.374, and then the formula is perfectly good. It's just going to be user error when we're measuring the time with t. I really think that's what it is.
Yeah. So you get a correct answer.
Yeah. Like I said, so if you that formula right there, that's at the letter I. If you try because obviously delta H is 0.54, like if we, you can do it, it should work. This should work for any 2 points because delta H is just the difference in height. So we did a difference of 0.54. And so the difference delta L, which is, x2 minus x1 is also going to be 0.54. That's not going to change. They're not going to be different values.
So the only thing is the k.
So yeah, exactly. So k is the problem variable. And then I tried to see what k would need to be, and k would need to be 9.37. And then if you go back to the formula that we got k from, the 4m times pi squared over t squared, in order for k to be 9.37, you just need t to be 1.09, which is only 0.04. 0.21 off from what we got. And I think, like I said, I think it's just because we were measuring it. Because we're clicking the timer, we're trying to pull it down the right amount. Like I think that's what's getting it wrong, because this should work out just fine. It's just k.
Yeah, I mean, just the experiment can have some errors.
Yeah, exactly. So if anything, I mean, can we just change? Can we just know that t, in order for this to work, t is supposed to be 1.09, and that k should be
1.09?
Yeah.
Okay, you can use it.
Okay, yeah, because then it works out perfect. If t is 1.09, that makes k 9.37, and then when you do the equation under I, it works out. Like if you want to do it right now, it'd be 0.258 times 9.81 times 0.54 equals 1/2 times 9.37 times 0.54 squared. You get the same. It's the same value.
Okay, so if anyone who are interested in trying, you can use t equals 1.09. So we don't want to spend too much time. But this one, you can definitely calculate them separately. You just list the results. You don't have to make them equal because there are some errors when we calculate the t. So yeah, I just very quick to go over the last few questions. So we'll be
done.
Thank you. Are you Winsor, right?
Yeah, no problem, no problem.
Oh, Alex.
It was confusing me too. I wanted to figure it out. It was bothering me. There's no problem.
Thanks. So then we can draw, make a table, the final table. You try to complete this table and draw two graphs. One is spring constant versus the distance. Another is periodic time squared, t squared versus mass. And so these two graphs are pretty easy because if you go back to look at this one, so so like one is to draw a graph of spring constant versus displacement. Another is t squared versus m. So you can see from this one, it's also like kind of related to the constant. And you know, and we know like from the constant, the spring constant wouldn't change. It's a property, physical property. So it will be so both these two lines will give you let's say t squared over mass. T squared over mass is equal to t. If we put a t squared and m on this side, can I still draw something? So if we put t squared over mass equal to 4 pi squared over k. And this is the constant. This one is also a constant. I mean, pi is constant, k is constant. So you get a constant, right? So the slope will be a constant. The second one, slope will be constant. And this one, constant, spring constant versus distance. And no matter how far the distance goes, then the spring constant will remain the same for sure. So you get I would assume like the first graph you get a straight line, and the second one is either, but the slope will be constant. This one will have a slope, a constant slope, like a. Then you can try from this. You have a mass different, and you have the force mg, just come mg, and displacement. So I go back to. So you can adjust 10 gram. Wait, can you adjust 10 gram? It's 50, minimum 50. Oh, yeah, you can adjust 100. Sorry, I'm just a little bit lost. Okay, this is 100. 100 is 0.1 kilogram. So you have the displacement. You just measure this displacement, and then you can calculate the spring constant by mg over x. So you have a spring constant. And the periodic time, you just use the timer to measure 10 oscillations, time for 10 oscillations per periodic time, which is divided by 10. So you then you measure these two unknown mass by using the spring constant, because from here the spring constant will be very similar, and then you use the average. You can take an average and you just pick the one that's most common appeared. You just take an average of all this spring constant and then try to calculate. So this two will be having the same spring constant. Then you measure the displacement and try to calculate the m. I mean, the force is equal to spring constant times displacement. Then you plot these two graphs. Then you'll be done for this one. Also, there's another question: determine the mass. Okay, what effect does damping have on the spring? So you have a damping. You have like energy. Like there will be this, not this here. Just you have energy convert to the thermal. Let's see. You have here. Let's see. Higher, more exactly. If I have damping, just like you have a thermal, it convert to like heat. So so without damping, then you can remain the total energy constant. With damping, you have the energy convert to thermal energy. So that is how you answer this question. So this is the last lab. So any questions so far for the table and graph?
No, just for the lab report. Is it okay if we just do the answers to all these questions, the data tables and the graphs? We don't need a intro and procedure and all that?
Oh, no, don't need that. Because this last lab is pretty long, so you don't have to write the procedures.
No, thank you. I appreciate that.
Yeah, I know also it's like
take a while.
Final. Yeah.
Okay, thank you. Yeah, that's the only question I had.
Just simplify them, answer the questions. Yeah. Any other questions? So our next lab report is due next Tuesday. Please submit as soon as possible, because then I will upload your grade to the no, I will send all your grade to the department. And if you have missed any lab report, please submit them as soon as possible. Or you have any questions about your lab report grading, you can write email so we can discuss. Yeah, thank you guys for the whole semester. Yeah.
Thank you as well. Appreciate your time.
Thanks.
Thank you. It's good to meet you.
So if we have any questions, I think that will be next week is our last lab, right? Wait, do we have a lab next week? When is the final? When is your final?
I believe it's the 24th.
Oh, 24th. If we want to have any, oh wait, Wednesday. Tuesday, sorry. Tuesday. If we want to have any recitations, we can have next Tuesday. Just let me know your questions. I think just like I'm playing a supporting role in the recitation. Some students are really active in the recitation, so I'm very happy like you guys can like work on that as a team. Yeah, just let me know. So maybe next week I'll see you guys. But it's not mandatory. If you prefer to work on yourself or with your friends, you're also welcome to do that as well. But yeah, wait, I need to take the screenshot for the attendance gallery. Okay, thank you guys. Have a good evening then. Bye.
Take care. Thank you.
Thank you. Bye.